Hi, I'd like to talk about map transformations, and this is a tool that used to be used a lot, not so much anymore, but it's still good to have it in your toolbox. It's to convert from a 2D to a 2D coordinate system where the original source coordinate system is an unknown or an arbitrary coordinate system, usually a map that hasn't been digitized, a physical document that you pulled from the archive somewhere, or an image screen grab from a planar surface. And the long and the short of it is we match control points, points that we can identify precisely in both the source and the target coordinate system, and then transform from the source to the target using an empirically fit equation. Why would you want to do this? Well, sometimes you don't have updated imagery while you have changes on the landscape. So here's a part of Duluth where they did some reconstruction along Canal Park. They've modified and put in new buildings. Here are the new buildings here with the old building footprints. And I want to incorporate those into my buildings data set, but don't have a recent image and don't have the wherewithal to fly a drone and get a high accuracy planar registered geocontrolled data set. Another common use is for old maps. So these are plat maps, and in Minnesota, they've all been converted and geo-registered using the process that we're talking about today, but there are many other old maps in archival storage, different places that you may want to geo-reference. This map, because it has the section corners, and I can find those section corners today, I could use those to pin the map down into a real coordinate system. If I were to scan this, it has an arbitrary coordinate system scanner, inches or pixels from the lower left or upper right corner, and those, I can't use a projection or some other method to get those basically pinned to a known set of coordinates. So the main points here, you use map transformation when you can't determine the coordinate system of a planar image or layer. So our clipped bit of Google imagery or our digitized or scanned or paper map. You add positional error to your data. So there's error in the drafting or error in the image acquisition, but because there's some uncertainty in the map registration and the control point matching that we use, we are unavoidably going to add some positional error. We struggle or really try to keep that error as small as possible. Basically, we match a sufficient, well-distributed set of coordinates. So how many are sufficient? 10 or 12, you should strive for 20 or 30. Beyond 20, you start to get a lot of diminishing returns. That they be well distributed is more important. That is evenly distributed around the image or the registration area as much as possible. There are different kinds of transformations, and the softwares often offer up polynomials, which by some metrics naively look like they're a better fit, but they're usually not. You're better off using a linear or an affine transformation. And you don't ever want to use this transformation process when you can do basically the same thing with a projection. If you know the input coordinates and you know the target coordinates, you don't want to use a transformation or a registration. You want to do the projection between those two known coordinate systems. So here's another example. This is actually something a graduate student used. They were looking at a time series of data, and they had time series of images from Eastern Europe that had never been registered. And so these were planar because they were taken from high aerial views with mapping cameras, but the earlier sequence of images from the 1930s to the 1980s had never been scanned or registered. So the students scanned them and then could combine them with current data that was geo-registered satellite data, but they had to get those data into a known coordinate system to do the comparison of this, in this case, the desertification and drying of a overused reservoir, right? So the main reason we don't reproject is because we have these screen or inch-based coordinates. And the transformation registers the image to a known coordinate system just knowing these screen or inch-based coordinates, and then for corresponding points, the ground coordinates, the target coordinates. We have to get those target coordinates, though, so we have to either have another image that has those coordinates or be able to visit them on the ground and GPS them, somehow get the real coordinates, right? So we need control points. Control points are these well-known points in both sets of images. They have to be map or image visible and precisely known. So we can always digitize them in the inch space on the scanned image or clicked image, or we can digitize them using a digitizing tablet on the paper document. And then we need to get the real coordinates. And so we either have to have another source that's been registered that we have the coordinates for, right? Another image that is from an earlier time but is georeferenced, so I know the coordinates when I pan about the image, or I should be able to visit them in the field and collect their coordinates. Here's the basis of what we need. We have the digitizer coordinates, and these are small numbers, 103, 100. These are some arbitrary coordinate system from the lower left corner of an image. And then we have the real world coordinates, the UTM coordinates that we've gone out and collected. So we're matching the coordinates that were on our scanned image that needs to be registered to a GPS reading, in this case, to get all our coordinates, right? You often struggle to get a well-distributed set of coordinates. They have to be identifiable in both the source and on the ground, or in one case, if we're going to GPS them, or the source and a previously registered image in another case. And so you sometimes have a hard time finding enough distributed around the landscape. If you find enough and struggle and can get them, then you can do this matching, right? So there's a correspondence between these. Now, what do you do when you have them? You set up a set of equations and estimate the parameters for the equation. So I have an easting, there's a translation factor plus a coefficient times the x and a coefficient times the y. So these are the x and y's in our arbitrary coordinate system, in our pixel or scanner coordinate system. Then these are the easting and northings that we GPSed on the ground, or that we got from another registered image, another georeferenced image. Same thing, the northing is equal to a northern translation plus 2 coefficients that are estimated. And these three things, the translation and the coefficients, are all estimated from the set of control points, right? The control points are known, so I know the easting and the x and the y, and then these parameters are unknown. So basically I'm fitting the model. Now it's a two-dimensional fit, but here I'm just showing it in one dimension, so I'm just showing the x and not the y. It's hard to visualize in 2 dimensions. But what I do then is fit an equation, and it gives me a plane here rather than a line. And from that equation, I can go in with any x value and calculate then what the easting value is. So I can translate an x coordinate to an easting coordinate in my known projected coordinate system. So I have to estimate this with the equation. Now, the software typically allows you to do the matching. There's an extra credit exercise in the lab portion of the course, so that you have an input and an output, or you can match to a list of coordinates. And it does this fitting for you, a least squares fit. And if you have 30 points, it just does it quite rapidly. It can actually do it on the fly as you go. And then it will have a transformation step. So there's a matching, a control point development set, and then an estimation set. You estimate the parameters of the equation, and then there's a transformation set where it takes your input image and runs it through your fit equations and does an output image in the new easting and northing value coordinate system. So 3 main steps. There's the control points, matching, the equation estimation, and then the transformation process. So here I have an image where you can see there's the road work, this is my control, and then there's the image in the background, and I'm going to match points, like these intersection points and these intersection points as I go along. So I match the control points. In some softwares, they do this interactively, so you'll match one and it fits it as best you can. You match a second, it'll unfit it a little better. You match a third, it'll fit a little better. Some you just submit the lists of coordinates and then it fits the whole thing. And so you can estimate equations. In this case, here's the equation estimates, and then apply it. You can see now the image more or less fits the roads. If we were to zoom in, we'll find some errors, but it's pretty good. Now, those errors I talked about are a mismatch between the observed coordinate, the coordinate you get from your control point, and the coordinate that's predicted. There's a deviation between those, and for the known points, we know both. We know the truth, and we know what we predict from our model, and so we can calculate an error for each of our points. Now, we want this error to be small and evenly distributed. If it's not, we need to go back and look at our control points and try and add more control points to figure out where we blundered. We often want to have a target for the root mean square error. We've got to be careful using the root mean square error, though, because it's kind of a dumb number. It only gives you sort of an average value. But when you look at the fit, you can usually, there's one or two that are way off. And since one is off by a lot, it pulls the rest over. So I would go to 4 and say, look, there's probably an error here. Go test to make sure that there isn't a mismatch in the selection, that I'm not at the wrong side of the road, or that I somehow misidentified the point, or go look at the original source of the coordinates, the true coordinates, because that's clearly larger than all the rest. Because that one's so bad, it tends to pull others off, like pulls 1, because this is big positive. This goes negative to try and correspond. The same thing here, this minus 18 for 9. I really don't want to just arbitrarily throw them out and refit. What I want to do is try and find out why that error is there. Is it a misrepresentation or not? If they are, in fact, in the right place, then I really should leave them in. In this case, let's just assume that they were misidentified and I deleted them or fixed them and refit the model and got a new model. And when I fit it, then I get this equation, and it gives me a root mean square error. Now, this root mean square error is a coarse measure of your accuracy. Another thing about the root mean square error is that it's in a way an average error, but it's an average error that's only applicable to the set of parameters that you've used, your set of control points, but especially to the kind of model you used. I can't use the RMSE to compare across different kinds of models. So this is just an affine, a linear model, where the x and the y are just, they're linear variables. It's not x squared or x cubed, and there's no xy interaction factor. If I have a different model, so suppose I had the e was a translation factor plus a parameter times the x, a parameter times the y, and another parameter times the x times y to see some interaction, I couldn't compare the root mean square error of that model to this model. It doesn't tell me anything about which is better. So you got to be careful that you don't compare across model types. And that's something a lot of people do, and it's a mistake they make. It's a mistake they make because they add, basically, in the software, other options, and the options kind of call you to do something that's wrong. Well, how many control points you need? Like I said earlier, 12 to 30 is a good number. And you need at least 3 in each of the quadrants. If you have 12, so you want 3 in the northeast, northwest, southeast, and southwest quadrants, right? You should have an independent higher order data set, something like 10 times better, to really test the accuracy, but you almost never have that. And so you fall back on the RMSE, but the RMSE is not a very good measure, particularly when you're comparing between different model types. With model types, it gives some information. Between model types, it gives no information. So here's the drawback. They give you higher order polynomials to use. If you pick a second or third order polynomial with the same data, the RMSE, by definition, has to decrease for higher order polynomials. But the fit is often worse. You get a more error away from your control points. These polynomials are so flexible, they can fit any set of points. But if you don't constrain your model at a location, the error from fitting at those points bends and really makes your data bad away from those points. So you shouldn't use a second order or third order polynomial, even though they're often provided. It's basically a result of engineers or computer scientists being able to write software without having a good appreciation of statistics. No statistician would do this, would provide this as an opportunity. As an example, here's a a first order polynomial with its root mean square error, 7.2, and a second order. These are the same points. I haven't changed anything but just changed the model type, and the root mean square error is 3.82. And then I get a first order and a third order. See, the root mean square error is 0.0003. You're thinking, oh, I have better than centimeter level accuracy. And that's true at the points you do, but if you look away from the points, you get huge deviations. So if you had independent points, the error would actually increase from the first order affine to the third order. And so you have to be careful. It's best to use an affine all the time, unless you have a special case and know better. All right, map transformation summary, it's from 2D to 2D. You only want to use it when you have an arbitrary inch space or scalar coordinate system as your source, and you want to get it into a projected coordinate system. You have to have these mutually identifiable control points. The affine transformation is best. To fit the affine, you really need 3 points in each of the quadrants, and from 12 to 30 total. And you shouldn't use this when you can use the map projection. When you know the input or source projection, then you just use the projection engine or a projection command to get it out to a different projection. So don't use this when you know the coordinate systems on both. You only use it when you have an arbitrary coordinate system to begin with. Hope that helps. Hope this tool at some point in the future may be useful to you.